Okay, let me now say the average for the graded score for test 3 is 80. Let me just double check. I don't want to. Yeah, it's 80. So then you can now know your own individual score relative to that, and then you know where you are relative to the average. Okay? Well, whether you count it out of 150, it does not matter because I have to decide on how to weight the how to weight it. But all you need to know is your raw score was out of 150 and the average is out of 150. But how do we regard it? I don't quite know yet for the moment because I will just add it all up for the whole thing in the end of the semester and then say that the average is equivalent to, I don't know, maybe it's a C plus, maybe it's a B minus, I don't know. All right. So you can kind of sense yourself how you did relative to the average. So this is, yeah, whatever it is out of the blackboard, which was 150. Okay. I know it's quite a stressful time for everybody, so it's not easy. Any other questions or comments? And incidentally, the final is on December 15th, and it will be live in Baskerville. You have to find out where that is. It's in the courtyard. Baskerville, room 210. I don't know the size of that room. I don't know where is that room because we usually are Marshak, and I've had classes in Shepherd, and in North Academic Complex, but I never had classes in Baskerville. So, but that's the assigned place, and it will start at 6 o'clock in the evening, and will end at 8:15. How's the Wi-Fi there? I assume it works. I don't know. But that's the administration. They just say you are now assigned that room, and I assume that if you've been assigned that room, that the Wi-Fi works there. I will send an email to the department and say, can they? And they will probably say, well, the school says it's okay. Say that again. What was that? If somebody what? But anyway, all right. So I will check and I will ask, but you just have to go on the basis that they will provide Wi-Fi. If not, then the school will have to do something. I don't know what. And also, I am not sure now what is the schedule for makeup lab. They have not yet given me because everything's in such a state of flux with everything else. So it's Baskerville room 210, not 212, 210. Please don't go to the wrong room. It's 210, room 210, Baskerville on December 15th. No, 210, 210. And the exam starts at 6 p.m. and will end at 8:15. And on the basis of 5 minutes per question, there will be just 27 questions, random block, blackboard. Attendance for recitation is not mandatory. The lab report will only focus on your lab report, whether you have handed in the lab report and so on. Okay. Any other questions? Okay. All right, so now I'm sort of doing a review already in a way because we have covered all the syllabus. We already did the matter wave in with the you know, wave particle duality. We already did that last time. So I'm now going back to electricity because after all, that's very important for you and me in our daily life, in your biomedical career profession. You will need electricity, you will need magnetism. So we need to review what we have already covered. And I understand that somehow this book, I am not that pleased with this book, but that's the book that we have been using for, I guess, so many years. But anyway, I'm now reviewing, and we came to the Coulomb's law, and I just want to remind you, nobody had a chat, that the key thing about electricity is that there is a either repulsion or attraction between charges, and like charges repel, like meaning of the same sign. If both are positive, they repel. If both are negative, they repel. But if they are opposite, plus and minus, oh, they attract. And the convention for what is positive, what is negative, came from Ben Franklin. But today, we understand that something is positive because they lost the electrons. Something is negative, or because they gained electrons. And when you're rubbing some of these things, a glass rod, well, the electron is easily removed so that it ends up being positive. It's not that these are now positive particles running around. It's rather these are atoms that originally was neutral. They had the electrons going around the nucleus very nicely, sweetly. But now, because somebody came in and was rubbing and grabbing my loose electrons, because there are some electrons that are far away from the family, and they got rubbed away. And so therefore, this now glass rod becomes positive. But if you really ask, how is it, what happened was that this rod, this glass rod, lost so many electrons. But each electron is so very tiny, 10 to the minus 31 kilogram, that you don't really see, you cannot find out just by weighing it, but you do know the reason why it is now positive is because it is lack of electrons. It is looking for electrons. So if I bring my glass rod here, it is now smelling, well, not exactly smelling, but it is now looking for, gee, is there an electron somewhere? And now, the concept, if there are, let's say, loose electrons, the other part is your fur and so on, they can become, the plastic rod, they become rich with electron because they grabbed extra electron as you are rubbing it. So if there are some rods or some source which indeed is rich in electrons, they produce electric field. That is the new language, which is the most big step forward from Coulomb's law. The biggest step in Coulomb's law is to now say, I now attribute, I take the Coulomb law apart, and I say the force that this Monsieur Professor, Coulomb, de Coulomb, what he measured, what he figured out was this inverse square law, but we now can re-express it by saying the reason why I am attracted to you is because you, electrons, you are the source of electric field, and the electric field lines are pointed to you. If I am lack of electron, I am positive, then the electric field flows out from me. The electric fields flow from a positive charge, who's really lack of electrons, from a positive charge towards a negative charge. All right. So we will now, from here on in, say that there may be a, oops, what did I do? There may be a source charge, Q. If it is positive, it's lack of electrons. If it is negative, it is, you know, surplus of electrons. And now, if you are over here, this you can call it a test charge, or you can just say a point charge. If you have somewhere over here, then you will feel an electric field on you, the electric field being produced by this charge Q. And if it is positive charge, the electric field is this way. If it is negative charge, the electric field is towards it. But for the moment, we just call it capital Q. So let's think of it as positive. Then there is an electric field due to your source. And you can now, Q is affected by your source. If I was absolutely neutral, I would feel no force, and Coulomb's law is irrelevant because I say I feel nothing. But it's because I have a certain charge, little q, then I am affected. And I now know, woo, if I myself am positive charge and you, source, is positive charge, I am being pushed away by you. You being the one that produced, or the source of this electric field, E. And we are putting the Coulomb's law. You remember Coulomb's law is just that whatever is the strength Q and capital Q, that it is inverse square law, 1 over r squared. And this is just the unit vector, because the electric field, so to speak, like radiate from your source. If I have a particular source, the electric field is in all directions coming up, and it goes all the way. If you were, at the GW Bridge, and the lab is in the Marshall building, oh, it's very, very small. Why? Because R is so big and it is inverse square R. But in any case, this is re-expressing Coulomb's law by saying that I now re-express it as little q, me, my charge, times the electric field that was produced by you. And the electric field produced by you is the Coulomb's constant, is a number, K, Q, your source, over R squared. So the most big step forward is the concept that we now introduce, electric field and electric field lines. All right, so I have put a shade on this basic formula so that whatever problem they may put to you and say that, oh, I have a charge here and it's located at this corner of the room, and I have another charge over there. What is the force? What's the electric field, and so on? You just work it out using these basic formulas. All right. And K is a number in these units, in these engineering units, in volt meter per Coulomb, and it is a number 10 to the 9. Oops, what happened? Yeah, it's a number which looks very big compared with Newton's constant. Newton's constant is 10 to the minus 11 in the metric units, in the international metric units, whereas this one is 10 to the 9. So you can say, wow, the electrostatic force is very big. On the other hand, the charges that we deal with your glass rod, with your rabbit fur, with your plastic rod, the charges are micro Coulomb. And 1 microcoulomb is 10 to the minus 6, and then you have another 10 minus 6, then you have 10 to the minus 12. So the electrostatic force is not that strong. And for us, the fact that the Newton's law makes us sit so nicely in my chair and you so nicely in your chair is because the Earth's mass is so much bigger than our mass. But anyways, this is then the Coulomb's law, which we now take the big step forward and say we want to introduce this concept that it is the electric field that now influences you, that influences me, that influences anything else around it. And so this is now a very nice picture that says a source of a positive charge is a source of electric field that radiates all the way out. Whereas for a negative charge, it is where all the electric fields are pointed towards minus charge, but away from a positive charge. And so if you were to put the two close together, what happens is the electric field lines will now jump over or go over from here to here, and that's how you can then trace what happens. Electric field lines or lines of force provide a map of the electric field in the space surrounding electric charges. So you can have whatever is the source, Q, and there will be now electric field lines coming out. All right, so this is one where it's direct, but here there may be some material shielding it. We will see, we'll follow through with the further development. Okay, and so we now say, hey, I want to now apply this concept. I apply this concept now to what we today now call capacitors. A parallel plate capacitor, where I have a plate which I have now charged to positive charge. In the old days, you would run it. But today, all you have to do is to connect it to a battery of a known potential. But in any case, that's the concept that I can charge this plate. And when I charge this plate, that it is positive and actually connected to a battery, then on one side, this is positive, on the other side is negative, because overall it was neutral to begin with. My original capacitor was originally neutral. And when I now connect it to a battery, then the positive charges flow over here because they came from the anode, and this is to the cathode. And what we have then is some positive Q that deposited in this capacitor. We are using the technical term. It's a capacitor. I have now positive charge Q and negative charge Q, and in between, we already have this concept that these are positive charges, and the electric fields, they come from the positive to the negative. And if you have a parallel plate capacitor that are close together, oh, the electric field lines just go say, hey, I can go straight across, right? Those that are near the edge, well, then my electric field are trying to go all the way around, but this is now being pulled over here, so I have my electric field lines that are sort of bent a little. All right, they will be bent like this, they'll be bent like that. But in the middle of this capacitor, they are all just flowing straight across. The electric field between two closely spaced, oppositely charged parallel plates is constant. And then later we will then want to go a step higher to follow this Gauss law, because Gauss law then tells us, I know what is the electric field coming out of this plate, and we will follow that. Electric dipole is just this, where I have a plus and a minus, and of course the electric field lines would now to want to join in to this side, want to join in on this side. And these guys are the ones that go far out and come back in. This guy, they go all the way to infinity and then they come back down to come this way. So they call this the electric dipole. You can map out the electric field lines, but we don't need to go into that. We just want to have this, appreciate this concept of the electric field lines, and we want to now go some more. Now the electric field lines inside a conductor, there are questions that can be posed, which is this thing called shielding. We already had that in one of the tests. I forget whether it's test 2 or test, yeah, must be test 2, where we had many such examples, and we begin to recognize that if I were to have, for example, charged a sphere and I made it overall negative because I have a plastic rod that was itself negatively charged, and then I bring it near to this sphere, and at first this sphere was neutral. The sphere was, it had no net overall charge, but now I bring my plastic rod and my plastic rod is negatively charged. When I now come near, because this is negative charge, then the positive part of the molecules, because now the molecules become distorted. The electrons, originally they were just going spherical, orbit, circular orbit around the nucleus, but because now there is an external electric field due to this plastic rod, then my electrons, they don't like those electrons on this thing, so they tend to be away from it, whereas the nucleus is more like, my good cousin is near, so the nucleus comes closer, whereas the electron in the loose orbit is further away. And so what happens is, now this surface that is close to this plastic rod is becoming positive, right? But if it is becoming positive, that means that the other side of my sphere is negative, because overall it was neutral. And now when I let this plastic rod, which was negatively charged, touch this sphere, if I let it touch the sphere, then all the electrons, excess electrons from here, will now be with this positive end and basically neutralize it. But this plastic rod has a lot more negative charge than this sphere. And so overall, I will now have given this overall sphere negative charge. I can now remove my plastic rod, and this now would be totally negative charge. Right? You remember that from the first part of chapter 18, I guess. We already went over it. And so the question now becomes, if this overall is negative, surface is negative, how about anything inside? For example, if let's say this sphere is not a solid sphere, but is a, what do you call it now? A hollow sphere, right? Then the question is, how are the charges distributed inside? Overall is negative. Well, inside, do you have any electric field? And we will then come to this understanding of Gauss law. Okay. Are you comfortable with what I'm trying to review for you? Under electrostatic conditions, any excess charge resides on the surface of a conductor. Because if, let's say, as a result of my, let's say this is negatively charged, and now I touched you, well, then of course what I touched was I grabbed your positive charges. Just think of it that way. I grabbed your positive charges, neutralized it, but I have a lot more negative charge than you. You are, after all, just simply a little originally neutral sphere. Whereas for me, my plastic rod is already fully, charged. So I have now neutralized your positive charge, but now there is a lot more negative charge available in my plastic rod, which I took away, and you now have lost so many positive charge, you are overall negatively charged. All right, so this negative charge of this will reside on the outer surface. At equilibrium, under electrostatic conditions, the electric field is zero at any point within a conducting material. And now you can say, can I understand that? I understand that the negative charges are all on the surface. You know why? Because negative charges, they hate one another. We are overall in this sphere now. We are all negative. So what happens? We all try to be as far away as possible. And given that it is a sphere, the only way to be as far away as possible is to be all on the surface. If not, I could be on 135th Street and you could be 137th Street, and then I still hate you. And you want to go further away, I want to go further away. So you end up, one end of Manhattan and the other one is on the other end of Manhattan, and one on this side of Manhattan, Hudson River side, and you are on the East River side, because we hate each other. We don't want to be close to each other, right? So the resulting remaining negative charge that is residing on this sphere will now be all on the outside, so that there is no more electric field inside. Okay, so now let us, this would be an example of trying to understand this from the field lines. We already have a capacitor that has positive charges. They are a source of electric field lines. And now on this side is negative charges. And these electric field lines, they now end on the negative charges over here. And then over here is the source of positive charges to go on to the other side of the capacitor. And this is then the picture of a solid sphere. But now if it is a hollow one, well, what happens is my electric field lines all end here, and then that's it. They don't go anymore because they have already been basically sort of like eaten up by the negative charges, right? The positive charge is the source of electric field line. Negative charge is the end point of the electric field line. So my electric field lines end here, end here, end here, end here. And then overall it was, let's say, neutral. Then there would be negative charge here. Then there would be positive charge over there. And they will be the source of electric field lines. And they go on to this negative side. And therefore, there are no more electric field lines. The electric field lines have been used up, have been eaten, have been absorbed. Okay, so you can say, see, the electric field inside this sphere, inside this cavity, inside this hollow sphere, the electric field is zero. All right, is it kind of, you can understand how to absorb, understand this now? We don't need to be a real, engineer, scientist to figure out the formulas for this or that. We just want to get the overall picture. And here they just want to say, to be more fussy, how does the electric field lines land on a surface? Well, they say the way they land is at perpendicular, is what you call normal to the surface. And later, when we talk about Gauss law, this question of how it lands is this thing that we then call electric flux, but we'll see. Okay, is there any question as we go along? I'm trying to review this now for you. Okay, so now let's go on, right? The electric field just outside the surface of a conductor is perpendicular to the surface at equilibrium under electrostatic conditions. Namely, it is not a current flowing, because if there's a current flowing, then the current can flow over here as well, but we'll see. All right, and a conceptual example, which I think you have done that in your problem set and also for test 2, you say, what if now I actually have a source inside this cavity or this hollow sphere, right? Now, if that is so, and if I am the source plus Q, it would be a source of electric fields, and therefore it would now land on minus charge, right? Because I have a source of positive electric field. The electric field lines will land and on these negative charge. But my original uh, hollow sphere was neutral. What happens is, if now on this side they are negative, then on the other side must be positive. So what you will find is that then you will now have the positive charges now on the other side of this hollow sphere, and then they will produce electric field. So then it looks like these electric fields came from here, and in a way it is, but technically it isn't. You got the picture, right? If I have a source charge inside this hollow sphere, I will know outside, because the electric field from here will basically grab, attract to it these negative charges. But then, since the original thing is neutral, there will then have to be the positive charge. It will be on the other side of this hollow sphere, and then they will produce electric field lines. So this is the sort of cute aspects of electric field, of the shield and of the conductor, of how some conductors can be a shield for things. Okay. A charge suspended at the center of a hollow electrically neutral spherical conductor, and now this charge induces charges on the outside. Well, this is a conceptual example, but it's a good review of the concept of electric field, and electric field being produced by a positive charge and landing on a negative charge. And in the language of these engineers, the number of lines, sometimes you can call it the density of lines, is in a way related to the strength of your source charge. The bigger the source charge, the more are the lines. It's sort of like I am radiating. I am now a big charge. I have, 5 coulombs, 10 coulombs. Then I will want to map out and show that these now become very dense, a lot of electric field lines. But if I am a smaller one, I may have only like this picture tends to imply I have only 1, 2, 3, 4, 5, 6, 7, 8. Is it 8? Yeah, I have only 8 lines. It's just a scale to say that the kind of electric field that I have from here is not so dense because my Q is not so large. But if my Q is bigger, I may have now, 14 lines or 18 lines or 16 lines, just to represent the fact that this is now more, the charge is stronger. Now we want to come to Gauss law. So let me just sort of emphasize again, Coulomb was very important for helping scientists to know the inverse square law for the forces between charges. But then when the scientists began to now split Coulomb's law into electric field and the force due to the electric field, then this electric field line now becomes a much more useful concept. But Gauss then makes an even bigger concept available. And what Gauss did was to say, I'm now interested in how much electric field is now coming out from this blob, this blob of stuff, right? Let's say there's this blob of stuff, because not all the time is it a sphere. For some of the problems, for Wiley plus, you say it's a sphere or it is a plate. But in reality, my charge may be inside this handphone, and this handphone is not in the shape of a sphere, it's not in the shape of a plate. It has corners here, it has holes here, right? And so what Gauss wanted to now do is, he wants to say, gee, is there some way of my giving a description of the law of electricity, electric field lines, such that I can now apply it to any surface? I don't need to be good with calculus. I don't need to be good with these actual equations that you have to work out. I would like to now formulate something which can help people get a sense, regardless of the shape. Well, so then what he introduced is electric flux. Because actually, when we come to magnetism, there was this magnetic flux. You remember? That's in chapter, is it 21 or 22? There's this magnetic flux. But actually, the precursor of magnetic flux, concept of magnetic flux, came from Professor Gauss, Friedrich Gauss, because he introduced this concept. I have electric field coming out. My blob, right? It may have some charge Q. I don't quite know how many. I don't quite know how they were distributed, because I was not there to figure out. I did not follow how you produce the charge inside. All I know is there's this blob, and this blob has a certain amount of charge inside, right? And now he says, but the charges inside are going to be the source of electric field. So there will be electric field coming out of this. In the previous example, it was a sphere, a hollow sphere. So electric field was coming out in a very nice, like radiation coming out of a body, a spherical body. But Gauss is now more interested in general. So he says, I don't know the actual distribution of charge in there. I don't even quite know how much charge there is inside. But I know how to measure the electric field, because we have now this nice concept, you can actually measure the electric field. How? Because I take a test charge and then I leave it in the presence of the electric field produced by you, and I say, oh, it is 3 newtons in this direction. You follow? F equal to QE. I don't know how much is the electric field. I can measure it. How do I measure it? I now say, I take a test charge, little q, and I measure the force on this little q due to this unknown electric field E, and I therefore know, oh, it is so many Newton per over so much is my test charge. All right. So he now wants to say, I want to now measure whatever is your shape, and it can be a googly, whatever, oblique kind of shape, right? I can now, as a experimentalist, measure. Gauss is trying to enable all engineers to be able to measure. I want to measure this thing called electric flux. And what is the electric flux? Electric flux is you take each segment of the surface and then you say, I measure the electric field. Well, because I know how to measure it, because F equal to QE. I know my test charge Q, and I have measured the F. Therefore, I know, oh, down here, on this part of the surface, the electric field is pointing this way. But Professor Friedrich Gauss, he knows that the way to measure this electric flux is the normal component. Is the perpendicular component of the electric field to the surface. All right, so he says, don't worry, I will measure the electric field and then I will take the normal component times the area and I will sum over it. I will actually sum over it. And you can have actually instrumentations that help you to do the sum, but the concept is I can sum over it. I can figure out what is the electric flux, and voila, he proved a theorem. And his Gauss law is a mathematical advance. Even in the calculus, it is a big step forward because this was before calculus was fully developed. Leibniz had already started and so on, but it was a big step forward in the language of calculus. There's this divergence of the electric field is proportional to the charge density. Don't worry, you're not going to be tested on it. But what is important is Friedrich Gauss was able to now say, if you measure the perpendicular component of the electric field coming out of any surface, however funny shape it is, whatever odd shape it is equal to the total charge that you have inside divided by epsilon zero. In other words, you want to know how much charge there is inside? You just measure the electric flux, and it is then Q over epsilon zero. So if you can measure the electric flux, the charge inside is the electric flux times epsilon zero. This then is what is known as Gauss law. Are you okay with this? I mean, it's not that we would then be actually doing in the lab with a funny, frog, and the frog's face has 2 eyes and so on. We're not doing that. All we want is first the concept that Gauss law now enables us to figure out many things without breaking this phone in order to actually say, I want to see how much charge you have. Let me break it out and go dig into it. You don't have to. Gauss says you can actually find out by, in some clever way, measure the flux. And if you can measure the flux, electric flux, you know the charge. or vice versa. If you know what is the charge inside, then you don't have to go and measure the flux. You don't have to go, oh, I take this little square here. Oh, what is this component? I take this little square here and do that. If you know what was the charge inside, Gauss says, I don't know how in German you say voila, but in German you say, uh, who knows German? How do you say voila? I know French is voila. There, you see, all you have to do is, if you know what is the charge in the charge inside, the electric flux is that charge over epsilon zero. All right, and now applications. Well, we can now do an application using Gauss law, and we want to now have, let's say, a shell, and the shell that is of radius r. Yeah, I mean, the book has this picture of a shell, and this shell has a inner radius r, capital R, outer radius little r. All right, and now first question you can ask is, what is the electric field outside? The electric field outside is whatever's the charge inside divided by 4 pi r squared epsilon 0. Why? Because the surface is 4 pi r squared, right? And the electric field is perpendicular to the surface. Therefore, the flux is E times 4 pi r squared, and that's equal to Q over epsilon 0. Right? So this is using Gauss law immediately. You just simply say, oh, you told me that this shell, the inner radius is capital R. I don't know why this book is so strange. They call the inner radius capital R. They call the outer radius little r. I would have been used to saying that this is, but anyway. So you now know that the electric flux coming out of this inside is the electric field at the surface times the area, 4 pi r squared, because that's a sphere, and that is equal to whatever's the charge that's contained inside the surface over epsilon 0. So outside the shell, this is the electric field. But now you can say, how about inside? Then Professor Friedrich Gauss says, you continue to use this, my law. And now the thing is, inside, there are no charges. All the charges were in the shell, right? So inside, there was no charge. If there's no charge, Gauss law says the electric field is zero. Why? Because Gauss law says that you can imagine taking what they call a Gaussian surface somewhere inside, but then you have no charge enclosed inside. Therefore, the electric field inside the shell is zero. Right? Do you see now the advantage of now using the Gauss law to figure out what is the electric field? Because let me go back to the Gauss law that we have. It is the flux. Flux is equal to what is the charge enclosed divided by epsilon 0. And flux is the perpendicular component of the electric field to the surface. And when you apply this more general formula to specific spherical shells, it becomes so easy. And the area of a spherical shell is 4 pi r squared. That's why the flux E times 4 pi r squared is Gauss law, is equal to Q over epsilon 0. So I have now very simply and easily made use of Gauss law to say, oh, the electric field outside a spherical shell, oh, it is like as if it is a point charge, all radiating from the original point. And yet it isn't, because inside the shell, the electric field is zero because there is no charge. The charges are all residing on the surface. Okay, and now you can come to here. That one was for a spherical surface. We can apply it to a parallel plate capacitor. A parallel plate capacitor is one where I have now this side all positive, this side all negative charge, and the electric field line will be shooting across. And now I want to use Gauss law to help me to figure out. So the book shows you three possible Gauss surfaces. They call it Gaussian surface because Gauss law says you apply it to any surface, and that surface that you use is now the Gaussian surface. And that Gaussian surface could be indeed your surface of this plate, or it could be this surface. So you can either use it as a surface inside this capacitor, or you can take a surface which is outside. And now let's try first surface 1. The surface is within the capacitor, within the positive plate. And now within it, there is no electric field. Why? Because the electric field all come from the surface. The charges are residing on the surface of this capacitor plate. So inside, there is no. Inside, the electric field is zero. The electric flux is zero. No charges inside this plate. Then we now take surface 2. Surface 2 is now the surface that is, you are taking a surface which is outside this plate. You're outside this plate. And when you're outside this plate, there are no charges there. So again, this is zero. The flux is zero because there are no charges here. Are you following what my mouse cursor is showing you? Yeah, it's sort of like it is a cylinder, but the surface itself is just the surface of the cylinder. And the surface of the cylinder is not embedded inside the plate, but it's outside. And now there is no charge because the charges are all on the plate, surface of the plate, but none here. So if you are taking a Gaussian surface, which is just a tube in this region, there are no charges enclosed. Therefore, the electric flux is zero. The net electric flux is zero. Another way of saying it is the electric field lines are all parallel to the surface. They are not perpendicular to the surface. So there is no net electric flux as defined by Gauss. But finally, you take a surface which is now containing this. So this is now a surface which is the full cylinder with one end inside and the other end outside, and you are now taking this surface, surface 3. If you take that surface, then within this surface is the charge on the plate, and phi E, the electric flux, is now E times A, because they are all perpendicular to on this side is all perpendicular. On here, the electric fields are parallel to the surface, So there is no flux and there is no electric field inside. We already showed that here. So the only side of this cylinder, solid cylinder, is the electric field on this side, which is perpendicular and times the area of the cylinder. So phi E is E times A, but now that is Q over epsilon 0 because you told me that you have this much charge. So it is Q over epsilon 0. Are you okay with this application of Gauss law?
So, Professor,
Yes.
will be the charge for the surface tree?
The surface here, there's no charge, but there's electric flux coming out. But this surface 3 is the full cylinder whose one end is inside, the other end is outside, and the electric flux is non-zero here. It is E times the area of this. And then over here, the electric flux is zero. Why? Because the electric field lines are all parallel to the surface. So there is no flux by Gauss definition. And then inside, there is no electric field. We already took the example of a Gaussian surface that was entirely just a disk inside, and there was no electric field, no charge, therefore no electric field. So the flux for the whole solid cylinder all came from this side, and that is E times A. Are you following what I'm showing you here?
Yeah, yeah, now I got it. Thank you.
Right? And so you can now say, whoa, Professor Friedrich Gauss, it's a very powerful tool. It's not just a powerful tool for the people who do engineering, but it's also a powerful tool conceptually to say, I now figure out a very fundamental formula for a capacitor, because this now says that the electric field produced by a capacitor is Q over epsilon A, right? That's algebra. The Gauss law is electric flux is Q over epsilon 0. But now I apply it to this very clever choice of a solid cylinder, and I now find that indeed E, the electric field for a parallel plate capacitor, is Q over epsilon 0A. But Q over A is the surface density. So the formula for a capacitor is that the electric field from a parallel plate capacitor is the charge density over epsilon 0, where the charge density is Q over A. It's a very powerful formula. And of course, Gauss law can be applied not just to a parallel plate, it can be applied to a concentric, plate and all that. And the engineers, they have to then, work with it. But we don't need to. We just need to have the overall grasp of Gauss' fundamental law and to recognize how it can be used to actually figure out the electric field in any situation that may be of interest. All right. Can we go on now? Okay. And now we need to go from, that was chapter 18, right? We need to go from chapter 18 to an even higher way. We already broke apart Coulomb's law into, electric field lines, and then the force on me is due to the fact that I have my little q charge. So the F is little q times this electric field line. But now we want to go even higher, and we want to now introduce something called electric potential. And a good analogy is to think of it used to be, well, even today, the weatherman always tell you there's a high pressure system, there's a low pressure system. Have you watched those weathermen? You know, they are so very good now to tell you things that help you understand when there is going to be a cold front coming through, when there's going to be a warm front coming through, when there's going to be a lot of rain and snow and so on, and wind. The main thing that we need to look at from this point of view, analogy, is the wind. Why? Because the wind will flow from high pressure system to low pressure system. This is the high pressure system. The air circulates around this way. And then this side is the low pressure system. And the wind will blow from high pressure to low pressure. What we introduce here now is electric potential. This potential, the surface, which maybe we have been using spherical surface or parallel, plate surface. This surface could be at a higher potential than this surface. And when it is at a higher potential to a lower potential, the electric field lines flow from higher potential to lower potential. All right. So here I take this diagram from Wiley Plus. We already understood by Gauss Law that in fact these charges here would be the source of electric field, and the electric field lines will have a magnitude which is the charge density divided by epsilon zero. So there is now electric field line that flow from plus to minus. But now the new additional concept is to say, hey, this is now an equipotential. It has a electric potential, and this is at a higher potential than this. And the electric field is always directed from high potential to low potential. You see how we have gone from single charge, capital Q is the source of electric field, and it is coming out from a positive source, capital Q. But what we are now beginning to do is to say, now I have many of those. I have, gazillion number of those charges, right? And now they are going to be all over on my surface. And in principle, my surface need not be a plane, parallel plate. It need not be a sphere. It could be this kind of a surface or some other kind of surface. Whatever is the surface, well, it will be a source of electric field now. We are generalizing, we are going up from Coulomb's law, which was from point charges, to now higher ways of looking at it. And we say, oh, you now tell me that there's a surface, and the surface is at a higher potential, then the electric field lines will flow from a higher potential to a lower potential. Uh, able to grasp that concept? Are you able to grasp that concept? Yeah, that electric field will be directed always from the higher potential surface to the lower potential surface. And if you now have a charge little q somewhere here, let's say you put a little charge q. Did they put a little charge q here? Yeah. If you put a little charge q here, as a result of this force law, this little charge q would then be pushed all the way to the other side, right? Isn't it? Because my poor little charge q, ooh, I was innocent, but you put me now in front of this plate of this equipotential surface, right? And you put me here, there are these electric fields. What do? They push me. They push me, they push me, they push me, they push me, they push me. How much work was done by this electric field pushing you across? Well, it is now the work done is the change in the potential. The work done is the change in the potential because you went from high potential to low potential, and this potential is a form of potential energy. So you now invoke this new way of looking at things from electric field to electric potential, and you now say that electric field is actually giving you from high potential to low potential, and the work done on any charge q, whatever is your q, the work done is your charge q times the difference in potential, difference in electric potential energy of this plate that has all these positive charges and this electric potential at the lower potential. All right. So this then is the new concept. You now say the electric field flows from high potential to low potential. And we now introduce this concept of electric potential energy because we already learned from 203 you can have kinetic energy, rotational kinetic energy, and gravitational potential energy, spring potential energy, but now you can have electric potential energy, which is the amount of energy that you now have as a result of having been pushed around, right? And you can now measure that kind of energy in what we call electron volt. Because for this, it's easy to do it in terms of the electron charge. And you say for an electric charge, if it has gone through 1 volt difference, the amount of work done is 1.6 times 10 minus 19. Electron volt is so many joules. All right. And it's a complicated slide, so I'm not sure it would be good to really go over it, but I want you to get the picture. The picture is that indeed we now introduce potential, electric potential, and then this is what we will not call equipotential surface, namely everywhere along here they are at the same potential. Everywhere along the surface they are at a given potential. And in the language of today, because I connected it to a battery and the battery is 12 volts, then this side is at 12 volts in potential, and this side is at 0 volt, so that it is overall 12 volt potential difference. All right, and so now we begin to have this new horizon. Why is that? We already said a point charge is a source of electric field. It radiates all over. Now we begin to say, if I have a point charge, it has a certain potential. It's like a gravitational potential energy. Then it has a certain electric potential energy, just like a mass in gravity. It has gravitational potential energy. Well, the definition of the electric potential is for a point charge is really a very simple formula, that it is whatever is the strength of your charge Q, and it will go like 1 over R. Just like in 203, when you learn about gravity, when you learn about gravitational potential energy, you first learn it as mgh. But then later, you find that in order to describe the satellite going to Mars, going to Jupiter, that you need to now introduce a more global definition of the gravitational potential. And the gravitational potential is 1 over R, such that the difference in potential between this point and that point reproduces Newton's law. So here, likewise, we now have a new concept. And let me again just say, we don't need to kind of follow how they do it. We just want to now say, I now begin to know Coulomb's law. The charges Q were a source of electric field lines. Yes. And then I began to now have this concept of Gauss law, so that I am able to now say whatever is the charge that is inside this whatever surface that I may be interested in, Gauss says the electric flux coming out of the surface is proportional to the charge enclosed inside divided by epsilon zero. But now, more than Gauss, I now begin to have a new concept of electric potential. The electric potential is, for a point charge, very simple. It is the same Coulomb constant times whatever is the source charge Q over R, such that when you are very far away, it is zero. But when you are close to me, man, the potential is very strong. All right. Now, let us now go on and see what are the neat things that you can follow. The neat thing is that this potential surface, every point along this equipotential surface have the same potential. And actually, this equipotential surface need not be spherical, need not be a plate. It can be whatever is the surface. If you happen to have connected my phone, to a wire somewhere, to a battery, then it will then make the surface, whatever is the shape, at a certain potential. Why? Because the charges will distribute such that in the end, everything is on the potential is the same, so that the electric field will now come from each part of my my surface, my phone, perpendicular to its surface. And so this electric field from here would be coming out perpendicularly, whereas from at the corners, it will come out perpendicular to the corner. So this then is the new equipotential surface. Then all the points along the equipotential surface, there is no difference. That's why the electric field is perpendicular to it. You remember how Gauss defined it? All electric fields are perpendicular to the equipotential surface. And you can now say, I can, for a point charge, it then, of course, gives me directly V is KQ over R, because I know my Gauss law. And K is the Coulomb constant. And the net electric force does no work on a charge as it moves along the equipotential surface, whatever its shape. And the electric field created by a group of charges is everywhere perpendicular. So if it is from here, it will go towards the lower potential. Inside, it's closer to this, so it's a higher potential. Outside is at a lower potential. And this is now the electric field line. So there are ways of now describing this electric field. It is really always flowing from high potential to low potential, and is always perpendicular to the equipotential surface. And now let us come to capacitor. Go back to capacitor, and we can now say, okay, we can figure out the potential difference in a capacitor, and we want to now describe what is called the capacitance of a capacitor, namely how much charge can it now have. I have a parallel plate capacitor, and I will now charge it, and I would like to know what is the relationship. Well, in the end, we will find that there is a proportionality constant, which is called the capacitance, such that given the voltage, and I have already, let's say, charged it with a 12-volt battery or a 15-volt battery, given the voltage, I'm interested in knowing how much charge have I given it. Now, you may ask, why would anybody be interested in that? In this formula? Why would anybody be interested in this formula? Do you know? I mean, just as it's a good daily life question here. Why would you be interested in knowing how much charge there is in this capacitor? Why would you be interested in knowing how much charge there is in this phone? Why would you be interested in knowing how much charge is in your laptop when you appear for the final? Why? It's a daily life issue, you know that? In our new generation, we always become very conscious. Is my cell phone running out of battery? Huh? Have you ever run into that situation?
Yes.
Is it not important issue?
Yes, it is these days.
Yeah. I mean, you go on wherever you want to go on a vacation. If you forgot to bring your charger and your phone is now down to 10%, then you would really be very upset because you're halfway on your trip and you no longer can rely on your phone. Or halfway through your final and you say, oh, what do I do? So it is important. You know why? Because the voltage is what your charger, like let's say you plug it into, I plug this into the power supply here. So it is the power supply here is 110 or 120 volts. And then I know it says fast charging. And then it will say, an hour or 2 hours for it to be fully charged. Then I know that it will then have, in the end, so many coulombs. Well, actually, it's not coulombs, it's millicoulombs or microcoulombs. I don't quite know how much is the charge. But the phone manufacturers, they know. The laptop manufacturers, they know. And they always want to say that the newest model, oh, is so much more powerful. It can do all of your whatever internet and whatever apps here. You have 15 or 20 or 50 apps in your laptop that you have loaded, and it is doing all of that even as you are doing your final. Well, there is this question of how much charge there is. Voltage is fixed because I use my power for here is PSE and G, or for you would be Con Edison. So V is fixed, and then what is fixed for you is this capacitance, because if your capacitance is large, the charge will be big. So it is an important issue, and the capacitance for the charger for this phone, different phones have different capacity. All right, that's why it's called capacity, capacitor. So you can now see it's an important question, not a uh, arbitrary question. It's an important question for our daily life. And the capacitance now is this proportionality constant that tells me that given whatever is the voltage which we employ, it tells me how much charge my phone has, how much charge my laptop has, and how much charge my car battery has, and so on. And the unit of capacitance is farad, uh, not because there is a Mr. Farad, but because there is a Mr. Faraday. Okay, so it's farad. All right. So now, interestingly, we can actually use Gauss law to figure out the capacitance. Now let us try it out. This is part of chapter 19. Incidentally, I put a this symbol just to say that it's important for us. Okay, now we already remember Gauss law, right? Gauss law says that if you have the on this side positive charge, on the other side negative charge, there will be electric field lines coming from this side to this side. This is the higher potential, this is the lower potential. The electric field lines will be directly perpendicular to the surface, and it is the charge density sigma over epsilon, which is of course q over epsilon 0a. I use little q. Should I have used capital Q? But anyway, don't mind that, right? I use little q. Therefore, this says that the amount of charge is actually epsilon 0a times E0. Whatever is the electric field, if you can measure the electric field, the strength of it, then I can tell you what is the charge. You see how I am using Gauss law to teach me things. Friedrich Gauss is so powerful, that Gauss law. I now am interested in saying, I want to know what is the charge on this plate. And Gauss law tells me, oh, you want to know the charge on this plate? All you need to do is to tell me what is the electric flux, or the electric field, times the area. So all you need to tell me is the electric flux coming from this side of this capacitor. All right. But now I also use work energy principle. Remember what the work energy principle says is that if I have a certain charge and it now is, I put it here, the electric field will push me all the way over there. And the work done is the force times the distance. The work done is the force times the distance. All right. And the distance is d. The distance is the gap. Let me say it again. The work done is my point charge, test charge Q. Well, I will have to call it Q prime or something. My test charge is being pushed by the electric field, because there's a force F equal to my test charge times the electric field, and it's now pushed across a distance d. Therefore, the amount of work done is my little q prime E0d. I cannot, I guess I will remember to, when I upload this, I will put in a q prime E0d. I put a note here for myself, all right? Imagine that I now have a test charge, which I call q prime, and I now say, how much work is done? Well, my test charge is being pushed by this electric field. It goes all the way over there, a distance d. So the work done is q prime E0d, which is q prime v. But for per unit charge, you can take away the q prime. Then this is now the potential difference. This is how we introduce this concept of potential difference, that this is at a higher potential, this is a lower potential. Therefore, E0d is V, the potential difference. And if I now take this, Q is epsilon 0, A, E0, but E0 is V over D. Therefore, the capacitance is epsilon 0, A over D. Therefore, the capacitance is epsilon 0, A over D. And that is showing you the power of Gauss Law. Because Gauss Law just says, you want to know how much charge there is? You tell me the electric flux coming out of this surface. But then we have now added to this Gauss Law this even higher view of potential surface. That this is at a higher potential, that the electric field will always flow from higher potential to a lower potential. And as a result, we now are able to figure out how much charge there is just by knowing what's the potential difference across. And this capacitance now depends on this distance d. It depends on the area of my parallel plate and inversely proportional to d. So that if my area is big, I can store more charge. That's clear. Even intuitively, that's clear. But what is not so intuitively clear is that I can store more charge when I make my d small. When I make my d small, I can make my capacitance higher. You follow it? And it came from this work energy principle. So this is then the important, crucial result of this chapter that builds on Gauss' law and now introduce this concept of potential surface, of electric field flowing from high potential to low potential. And you now are able to tell people, gee, I know my phone can store this much charge. Now the book actually goes on to dielectrics, but I decided that it's not you do not need to know, except to know that there is usually, it's not vacuum. What Gauss law here is for vacuum, but what the engineers actually use most of the time is a dielectric in between, and then there are this dielectric constant. So, but we're not going to worry about that. Okay. And it all came from Gauss law. And now, okay, we quickly go through. You have, of course, now electric current. Now that's easy. You already know that if I have a charge flowing at a certain rate, that's the current, and it is measured in amperes. And for currents in chapter 20 now, it is this relationship that says that the voltage across and the current that flows, they are proportional to each other with the resistance. If I have a big resistance, given that it is only 12 volts, my current is small. But given 12 volts, my resistance is small, then the current becomes big. And it is because of this relationship that says that beware. If for any reason your circuit has a short circuit, one of the wires inside your microwave oven, if one of the wires of the microwave oven somehow begins to, you know, uh, they were supposed to be very well, connected to the other part A to part B to part C. But if one of them suddenly, let's say, sags, and the resistance now is small, the current shoots up. And when the current shoots up, you're going to have a potential hazard. But anyway, this is the important Ohm's law, that the voltage across any device, the current that flows in that device, is proportionality by this R, which is measured in ohms, and the symbol for it is omega, capital Omega, Greek letter capital Omega. And then there's this resistivity, which is that a wire with a certain length L, the longer the wire, the bigger the resistance. The poor electrons, they have to, shuffle through this wire from one end of Marshak building to the other end of Marshak building. So the total resistance of this wire is proportional to the length of the wire, and it is inversely proportional to the area, because the area, if it is broad, then my electrons are not so squeezed, so they can go through, so that the resistance is less. And this is called resistivity, which the engineers will measure for all the materials. We don't need to know, but for us, we need to know this. We already know V equal to IR, but for us, we need to know this, because this tells us our device, our hair dryer, our phone, they are consuming a certain power. They are consuming a certain amount of energy per second. And the amount of energy it consumes, the power consumed, is IV. If I have a hair dryer, if you look at the label at the back, they will tell you, oh, this hair dryer is rated at 1500 watts. What that means is that it will be using up this much power, from Con Edison, 1500 watts, but its voltage is given. Voltage is 120 volts. Then the actual current that flows inside this hair dryer is given by this. So if I know this one is 1500 watts, and I know I'm using 120 volts supply, then I know the amount of current that is flowing in here. And because I know the current that's flowing in here, I know V equal to IR, I actually can also figure out the resistance of this hairdryer. But you can say, no big deal. I would not be interested in the hairdryer, but you will see later on, we will come to a reason why you need to know. And many electrical devices are actually resistors, so that the power consumed is I times V, which can be written as I squared R, or it can also be written as V squared over R. They are the same. They are equivalent, because V equal to IR. All right. So for electric power, the basic formulas are P equal to IV, and P equal to I squared R, P equal to V squared over R. And now there is still a little time. I just want to quickly now tell you a real life thing that we need to learn. You have your laptop. And of course, when you have a laptop, you go overseas. At least you're not going to be all the time confined. And for the laptops or your chargers, the people who manufacture these, they have designed it so that it doesn't matter whether you are in United States or in the rest of the world. United States, all the voltage is 120 volts. Overseas, it's 240 volts. Right? No big deal. But it's a big deal for your hairdryer because after all, you want to keep yourself, you want to, especially if you go for some meeting somewhere, right? Well, if you bring your hairdryer over there and if you plug it in, you can after all use these adapters so that when you travel, they tell you these international plugs are different shape, but that's okay. People sell you those adapters so that you plug it in. You go to the hotel, you plug it in. The problem is your hairdryer is meant to be operating at 1500 watts with 120 volt, right? For whatever's the resistance. But now the resistance hasn't changed. You are still the hairdryer, but your voltage now over there is double. It's not 120 volts. It's 240 volts. It's double. Therefore, what is the power consumed? Is it still 1500 watts? Or is it now? Huh? How many times? Are you following my train of thought for the it's a good thing to know. In America, it was 120 volts and this hairdryer works very well, very nicely. But now I plug it into hotel in Paris. It is now 240 volts. So what is now my power that I'm consuming? Huh? Is anybody awake? Or is it too late now?
Can you repeat the question, Professor?
Yeah. I have this hair dryer. It was rated at 1500 watts. I use it. Very nice. Now I'm overseas. I check into my hotel. I need to, you know, wash my hair and I use the hair dryer. I plug it in. But the power there, the power source, the voltage is double what is over here. Therefore, is the power being used by the hairdryer when I plug it into Europe, is it still 1500 watt or is it now 6000 watts? You
It's
following my question?
doubled, 6,000.
Huh?
I think it's 3,000. If it's like 1,500.
Is it double or is it quadruple?
Oh, it's gonna be quadruple, yeah.
Quadruple, you see? And so now that's the lesson. When you have your hair dryer, don't plug it in the room, because if you plug it in the room, your hair dryer is gone. It will basically burn out. But the hotels, they know, they welcome people from America, and what they have is in the bathroom, you will find that they say down here, this is for 120 volts. And if you plug it in there, they have a transformer so that the source there is not 240 but 120. So it's okay to plug in your hair dryer in the bathroom, but not say come out and now plug it into the hotel, by the TV, by the whatever you are watching, and then try to use the hair dryer. You will be destroying your hair dryer. And it is all this very simple formula. Nothing more than this simple formula. All right. Now, okay, I think it's time. Uh, well, it's what, 6:40. Uh, well, this is just a question of root mean square. I don't know. Maybe on Wednesday I will quickly summarize this, and then we can go on to magnetism. It's now 6:40. So, any questions?
Professor, will you provide any practice questions for the final?
Any practice questions? Well, I am still working on the final, so I cannot say, but it will be in the same style, all right? But
Sure.
27 questions, yeah? It will be in the same style. But I will have a review on December, yeah, next Monday. I will have a review, okay?
Okay, thank you, Professor.
Okay,
Bye.
all right. Yeah, good night. Oh, let me stop the recording.